we just covered all the integration techniques. But before we move on to the next section, I want to slow down a little bit and we're going to do a recap of how you have learned so far. In the second section, you learn how to estimate the area using the Riemann sum, which is summing up all the rectangles between a function and the x-axis. And if we subdivide the interval into infinitely many subintervals, then we can calculate the exact value of the sine area. So from this section, we learned that the sine area over an interval, for example 0 to r, by the definition it is the limit as n approaches infinity, and n is the number of subintervals of the sum of f of xk, which is the height of each rectangle, times dx, and the summation starts from k equals to 1 to n. Then in the third section, we learn a new notation, which is the integral. And from there, we start to denote the sine area as integral of the function f of x dx. And in the third section, we also relate what we learned in Calculus 1 to Calculus 2. In Calculus 1, you learn the derivative. And the sine area, or the integral of a function, it is the antiderivative, which is equivalent to the integral. So from this section, we got a lot of basic antiderivative formulas from the derivative formulas that you learned in Calculus 1. And then in section 4, we learned 3 basic integration techniques. First one is U-sub. Then the second one is algebraic method, including splitting the numerator or expand the integrand. Another technique is to complete the square. And the third technique in section 4 is when you have a rational function and the degree in the numerator is greater than the degree in the denominator, then we can use the long division. The numerator, n of x, divided by the denominator, d of x. And in this section, we've looked at 4 techniques of integration, with many cases for each of the technique. The first one, we look at the integration by parts, and we derive the integration by parts formula from the product rule from Calculus 1. And we also look at the reduction formulas, which is finding a pattern using the integration by parts. Then the second technique is trigonometric powers. There are 6 cases for this technique. The first technique is when we have odd powers of cosine function. And the procedure for that is we want to take cosine of x, dx aside, and that will be the du at the end, and use the identity cosine squared equals to 1 minus sine squared. And we are going to let u equals to sine of x. The second case is similar to the first case. It's when we have odd powers of sine function. When we have odd powers of sine function, first we are going to take 1 sine function aside with dx, then use the same identity. Sine squared equals to 1 minus cosine squared. And we are going to let u equals to cosine of x. And for the third case, when we have even powers of sine function and cosine function, we are going to use the identity cosine squared of a equals to half times 1 plus cosine of 2a. And for sine of a squared, the identity is half times 1 minus cosine of 2a. Then the fourth case, when we have odd powers of tangent with some secant function. Similar to the first two cases, the procedure is the same, but now we are going to take a tangent times secant of x dx aside and use the identity tangent squared equals secant squared minus 1. And we are going to let u equals to secant of x. Then the fifth case, when we have even powers of secant function. First, we are going to take 1 secant squared aside with dx, then use the same identity as the last case. Secant squared equals to tangent squared plus 1. And let u equals to tangent of x. In the last case, which is others, which means when the first 5 cases fail. When the first 5 cases fail, we'll need to do some trig identity, cheat, or guess. Then the third technique that we learn in this section is the trigonometric substitution. And for this technique, there are 3 cases. The first case is when we have the form of a squared minus x squared. The procedure for that is we're going to let x equals to a sine of theta. And we are going to use the identity 1 minus sine of theta squared equals to cosine of theta squared. The second case is when we have a squared plus x squared form. The procedure is similar to the first case, but now we are going to let x equals to a times tangent of theta. And we are going to use the identity 1 plus tangent of theta squared equals secant of theta squared. Then the third case, when we have x squared minus a squared form, we are going to let x equals to a times secant of theta. And we use the same identity as the second case. Secant of theta squared minus 1 equals to tangent of theta squared. And finally, the last technique, partial fraction. If the denominator contains distinct linear factors, using the partial fraction decomposition, we can write that as a constant over the first linear factor plus another constant over the second linear factor. And you do the same for all the linear factors. The second case is when we have repeated linear factor in the denominator. And the decomposition for that is some constant over the repeated factor plus another constant over the repeated factor squared until when you have repeated factor to the power of k. In the last case is when the denominator has a non-reducible quadratic factor. And the partial fraction decomposition for that is a constant times x plus another constant over the non-reducible quadratic function. That is the end of integration techniques. In the next section, we'll look at applications of integration.